Hello, I'm MC Toon, worst rapper in the world. Tonight we have a special debate or discussion here between a couple guys from Facebook that are in the group. We just lost one. They're in the group Logical. Matt, what's the name of the group? Logical something. It's long.
Let's see. Logical. Shoot. Well, I done forgot actually.
He made the group.
We changed the name of it so much. It's like logical scientific approach revealing the truth of the universe.
There you go. All right. So backwards way to introduce, but that's Matt Duckworth, who will be representing the globe tonight. How you doing, Matt?
I'm doing great.
All right, and then we've got Zechariah Edwards representing the flat Earth. How you doing, Zachariah?
Very good. Thank you for having me.
Yeah, it's good to have you both here. Let's take a minute to do some introductions. They already know that I'm the worst rapper in the world, but they probably don't know enough about you. So, Zachariah, you want to start?
Sure. Yeah, I'm just a normal guy investigating flat Earth for a couple of years now, and I come at it more of a scientific perspective. So I'm not going to make any friends here tonight. Not going to make any flat Earth friends, I'm sure, or globe Earth friends. But I just want to present my hypothesis of how I perceive a possibility for the flat Earth could, scientifically be possible. And in doing that, we're going to study Einstein's general relativity and understand how space-time moves through the universe, how we perceive everything around us from a relativity perspective. It all depends on our position in the universe, what we see. What many scientists see as a globe, they're observing from outside the universe and they're looking at it down. But me as a non-scientist, layman, I have to look at things from my perspective, which is here on this flat plane, what I perceive as, flat Earth. But I'm sure there's a lot of people out there who don't agree with that. And the reason why is because science has really taught us, it might be a globe. We have curves. We have all that. But tonight I'm here to present to you a possibility where relativity could play a huge role in what we perceive as the Earth moving through space, when in fact it could be space-time, moving through the Earth, through a flat Earth. From my perspective, if you were to stop time completely, is how I hypothesize this. If you were to completely just stop time, you would see everything, all matter, just stop in place. There would be no gravity, nothing to pull them together. So time is actually what causes gravity in my view. From a general relativistic point of view, we have this idea that time moves through space, and it's actually space that's being created by time. And without that space, matter would not form. Without the time, you wouldn't have any planetary motions of the bodies or anything like that. So this is just more of a general theory of relativity, where you have a Euclidean flat plane, and you don't have any non-Euclidean. Basically, how science sees the universe is as a warped CD drive, right? You have a CD drive and it's very warped, and that's how they get their round motions, their round balls going around each other, because it's being warped around by on a, say you took a disc, a flat, one of those old soundtrack discs, and you took that and you put it outside in the hot sun and it would warp. Well, now you put a globe on it, or a ball or whatever, and you mounted it there. That's how they see the whole universe spinning around like this. And I don't I don't see it that way. I see it as we're all in a Euclidean flat plane with the universe. You have black holes based on Archimedes' principle of buoyancy, right? Did the densest matter sinks below the lightest matter. So black holes would be the densest matter, but you also have space-time curvature pushing those black holes out. This is just a hypothesis, and there's nothing you can always say, oh yeah, that's not true. We can't test it. Okay, we'll see. We can look at it from a scientific perspective and see if we can test it. What I'm presenting here tonight, though, is the idea that these black holes are the highest density matter, and they have centrifugal force. And with any wheel, the centrifugal force pushes the dense matter out, out from the axis of rotation. So this is my idea, is that these black holes are quantum entangled, or what they call quantum tunneling, right? And you have the quantum tunnel connected to the stars, basically. So I could imagine 3 black holes spinning around the Earth from the bottom, centrifugally forced out from the flat plane. And then the stars, you have counter-rotating stars quantumly tunneled or tangled with these black holes through the center of the Earth. And this is just my imagination, a hypothesis that I see might be possible based on the scientific evidence that I've researched. But go ahead, Matt. It's
No,
up to you.
I'm sorry, I was losing you for a second.
Yeah. You did get just a tiny bit like we weren't getting a strong signal. We heard what you said, but your screen froze a bit. So, but we heard you fine. So,
okay.
Yeah. So, but that was good. So before Matt, you go. John Rapp says, "G'day, MC Tune. Oh look, I'm following the smart people around. Hopefully, it will rub off on me." So apparently, some other smart people were in a different stream. Maybe, I don't know. So, all right.
Cool.
So that was a little more an introduction. That's fine. So Matt, why don't you do an introduction, and then if you want to just go right into a response.
I'll be short. Again, I'm Matt Duckworth. I have a side as well. I'm a serious scientist. I get on my background. I know I have physics degree. I won't go into all of that, but yeah, I was trying to understand what you were trying to say. If you could, if you want me to go into more of an introduction, I can. But I'm really kind of interested in what he was trying to say. If we can go into that, but if that's all right, McToon.
Sure.
Can you explain a little bit more about what you were saying about the black holes? You're saying they're underneath the Earth.
So I perceive them as starting out from the singularity, right, the Big Bang, underneath the Earth, and then just because of the Big Bang, how you have this singularity with the mass, and then I perceive it as centrifugal force or centrifugal force, pushing those black holes out and kind of fanning them out. So it's more of a pyramid shaped,
So by believing in the black holes, you're saying you do actually believe in gravity itself.
Yes, gravity as an effect, which is different from gravity as a force.
So okay, it's an effect because it's created by the space-time curvature, right? In the introduction of mass. And in a curved space-time, or in space-time, which is by the introduction, is what creates the curve.
Right.
And the effect that we
feel.
So
the mass actually creates the curve, right?
Right.
On space-time.
Yes.
Warping the black holes, and it's a centrifugal force, or centrifugal. How do you say it?
So what
I'm
is the
sorry.
force that you're saying is actually?
I
Okay,
say
you got the black.
centrifugal is how I pronounce it.
Centrifugal. Okay.
And that's
All
what
right.
pushes it away from, the center of where it's spinning around.
So
Right.
how is that not a force? Okay, is what I'm trying to say. What force is there? If you're not saying gravity is the force, then what is the force that is causing things to move away or move towards?
Right. I would say that would be time itself, right?
So time is pushing it away. So now time is the
Time.
force?
Time is a force that's causing matter to, what do you say? Expand outward, right? So if you had the singularity, the black hole in the center from the Big Bang, right?
Mm-hmm.
And you were to explode that into a universe, it would be curving because it turns from energy, pure energy, into matter, heavy, dense, very hard matter, right? So it's the matter in space time. Just say you plop it inside the space time,
Uh-huh.
and it would be that and then for somehow all that energy just blew out in space time and started curving. You see what I'm saying?
Okay. All right. I'm somewhat following you on what you're trying to say, but why are you saying that time is a force and gravity is not? Is where I'm trying to lose you. I mean, why are you afraid to actually call gravity a force?
Well,
Time has nothing. I'm not trying to be rude.
no problem.
I'm just saying, time has. Okay, space time. Gravity is an effect. It is. It's created through the introduction of mass into into space time, which is why it's curved. Okay, and
Right.
that it's kind of like dropping a bowling ball onto a trampoline. We'll just say that. Okay, and the effect that you feel is what we would consider gravity. All right.
Right.
Now,
So
gravity does.
we're falling into that black hole is what I'm seeing, but it's not us actually following. It's actually space time following. You
But you're
see?
saying that time is what actually pulls us through the black hole?
Yes. If you were to stop time completely, right, everything
Mhm.
would just suspend in space and nothing would move at all. It wouldn't be. So time also gives matter substance. It gives matter, form. If
Right.
you, which you're a nuclear physicist, right?
Yes.
Decay over time causes matter to lose its mass. Okay.
Right.
So that's where I'm getting that idea from.
Okay. Um, I don't even know where to start with that one. Um, time. Okay. Time is not okay. I'm just going to say it outright. Time is not a force. Okay. Time is just part of a dimension. Okay. You have it's one of the four. It's part of the four dimensions. Okay.
So I
All right.
wouldn't say time. Okay, yeah, I'm sorry. I said time was a force. Time is more of a cause of the force, is what I meant to say.
I mean, I totally agree with the fact that gravity does affect time, and time is actually relative. And the way you're discussing it or trying to explain it, you're saying that time is the same throughout all of the universe. Um, Maybe we should
No,
actually.
no. So I understand time dilation, and with
Yes.
time, right? With
Mhm.
time dilation, I understand that as you get closer to the center of a black hole, you slow down. Time,
But that's
or from
because
our perspective, anyway. Yeah,
yeah, gravity affects
everything,
time directly.
right. Everything slows down from our perspective, but in the black hole, you're actually being warped really fast, I guess,
Okay,
into the black hole.
let's. I think we're getting stuck in a black hole a little bit. So, um, how is this black hole actually affecting us directly? You say that there's two of them, right, underneath us?
Maybe more than two. I don't know how many. I
And
hypothesize
what does that
it
have to
started
do?
out underneath us.
But why is that? Okay, if you're actually saying that actually gravity does exist, why are we flat? All right.
So I believe that it's
The
the
reason why,
centrifugal force that's pulling us, the whole universe outward.
right?
As it spins through space, that's flattening us out. And have you heard of Pangea?
Or you're saying that? Yeah, I know what Pangea is. Yes.
Okay.
Okay.
Yeah. Oh, sorry. I don't mean to. But anyway, with Pangea, that's what I feel is a centrifugal force causing it to spread apart. The continents and everything. And that's how I perceive the flat world to be Pangea. Before it started spreading out, and then space time with the black holes just kind of pulled them all apart and flattened them out that way. And I'm trying to understand how this would work on a globe. I really am. I promise you.
Okay. Do you
I
know
consider this
how?
on a globe as well.
Okay, because I remember we have talked before, and I've read some of your things, and you do admit that some things are round. Some of the planets are round, right?
Right. Yes.
Okay.
I believe in
Do
gas.
you know
I believe in
why
space.
they become round?
Yes. So I believe that in a vacuum or in a near vacuum, which space is, and I'm not one of those flat earthers who say space doesn't exist. I do believe that
I
there
appreciate
is there is a space out there. It might be within our dome, but it's still a space. And I believe that fire will burn around in a circle because they're gas giants or
Mhm.
plasma, you know. And I don't believe they're being pulled around the Earth or the sun, like I don't believe the moon is being pulled around in a perfect falling orbit around the Earth. I believe it more to be buoyancy causing them to float above the atmosphere of Earth, if you would.
Well, I do want to actually get into that and understand how buoyancy is affected in space. But okay, let's
Can I
understand.
interrupt just for a second?
Please go ahead. Go ahead.
So one of my favorite flat earthers is named Earth is Seriously Flat, and he has a super chat. He has two of them. First one is he's asking how to verify if something is light years away, and I know that's one thing that was maybe the second topic, so we can hold that off.
Yeah.
We can.
But
We'll
so
get
then,
in a tangent.
Then he comment. Yeah, let's not tangent on that. But then he comments. He's blaming. He says globe zombies blaming gravity, biatch for everything. So there you go. Earth is seriously flat. All right, continue.
Okay. No. Did you want me to respond on something on that?
No. It's comic relief.
Oh, I got you. I'm sorry. Yeah. Okay. What I would like to do, if you real quick, Zach, I'd
Sure.
like to see where we're at. Okay. So are we talking geocentric? Is that where you believe where the Earth is in the center? And
So, in a relativistic, sorry.
The sun is in the center. I'm just wondering where. Sorry, my phone is going crazy. Tell me where we're at. So I want to find some commonality, I guess you could say, so we could try to understand. So are we talking geocentric? Is that where you're talking? Where that means that the Earth is in the center of the universe, and everything else kind of flows around it, or are we, or do you believe that the sun is in the center and we actually, you know what I'm talking about?
Right, yes. So
Okay.
I believe it's all a matter of perspective. If you're stationary in space-time somewhere and you were stopped and everything was flowing around you, you would see a big spiral mess, basically, where we're like a million light years out and spinning in the galaxy.
That's not what I'm
But
talking. I mean, I'm sorry. Go ahead.
okay, sorry. From my geocentric point of view, I think from our position, everything spins around us. That would be
we're in the
correct
center
assumption.
of the universe, is what you're trying to say, or at least in the solar system, right?
From our perspective, yes.
Okay.
It's all a matter of perspective, basically. Relativity.
Well, everything is perspective. I totally agree with that. but I'm not understanding. There's a lot of things I'm not understanding.
Yeah. For the sake of simplification, we could just say that we're on a geocentric flat plane, and space-time is
on track. Because I mean, you did mention the Big Bang, and you do agree with the Big Bang, okay? Right. But you're not saying, but you're saying that when it exploded, gravity had nothing to do with how we actually got put together. Because you're saying it's not a force, and that how things become round are because of gravity. That's the entire point of it all. When things actually spin really, really fast, and get there, they're actually pulled toward the center of gravity. It's not definitely not just the actually, but that's how planets are actually formed. Things spin.
I agree with roundness in the form of circles,
actually spins around the barycenter of every single planet has a barycenter of around the sun. That's actually what technically planets do not actually orbit the sun directly. It's actually the barycenter. They have actually a point where they're the push and pull between each between the planet and the sun actually finds a the center of gravity, and that's where they actually are. And maybe we're getting on a tangent on there, but that is
interesting. I like
that. That's how they actually orbit. And if I do use a word that you don't understand, please let me know. I'll try to explain it a little better, and I apologize. But so I am a little bit confused, because black holes, you know how black holes are actually created, right? Whenever, red giant, suns, start losing their fuel over time, they get bigger and bigger and bigger. They turn into a red giant, and they either turn into a black hole or a white dwarf. Basically, they get so big, and then they either fall in on themselves, which is because of gravity. It's the force, that actually, they pull in on. Golly, sorry, phone is just blowing up. I know, I'm sorry. It's because of this. Anyway, it's turned off now. But I mean, I feel like there's either you're just outright ignoring, you don't want to believe in that it's a force, or you're trying to actually change, make it to where you don't want to actually believe it.
Well, I think of it more of Einstein, right?
No, I'm Einstein, definitely. Let's go into the general relativity. Let's go into it. Go ahead.
Okay. So Einstein says that gravity is a force of an effect, basically, of space-time curvature acceleration is his idea. And
yes, completely.
And he's like, no, Newton, mass is all relative. It's spinning around. They're spinning around each other.
Not relative, but I'm sorry, I didn't mean to interrupt you. Go ahead.
He's basically saying, okay, we got these things fall to the earth, right? Things drop to the earth, and it might not be because of a force of the earth pulling the mass to the earth. It might be the earth accelerating upward, right, up into the mass. And this is relativity, and on a Euclidean plane.
That's more of the frame of reference.
Right, frame of reference. So if you're thinking of the frame of reference of a black hole, and you're seeing we're all gravity around it, my question to you would be, how is it round? Because the axis, right, goes up and down, or it's spinning around the axis, right? Wouldn't the centrifugal force throw the heavier, dense mass out, away from the center of mass, from the spinning force?
I'm sorry, say that again. I'm sorry.
So my question is, wouldn't you think that when something is spinning in space, like a planet
Right.
or a black hole, wouldn't
Okay.
the heavy mass be pushed outward? Like a bike tire, you know how the heavier
You're doing
mass
this mass is being pushed away.
pushed, yeah, wouldn't it be a blade, like flattened
Yeah.
out, sort
Yeah.
of?
Well, it's an oblate spheroid
Right.
is what
So,
the Earth is actually. That's the
oblate.
actual shape of it. It's an
So
oblate.
I don't disagree that there is some sort of curvature to the Earth at all. I don't disagree with that. Okay, I don't think it's completely flat, but I think the bottom is misrepresented as the rest of the globe when it shouldn't be.
Right. Okay. Um.
Can you explain that a little more?
Please.
Okay, so you have very dense matter that sits on top of the surface of the Earth, right? Um, but it's not as dense as the matter underneath the Earth. And I don't see anything as existing below the densest part of the matter because of our Archimedes principle of buoyancy, right? I see that we have the north, the south, the east, and the west on a dome, on a dome of the Earth that's not completely flat, but actually a bit of a curvature to it, and then underneath it, I see as an abyss and a black hole, or really dense, hard matter that everything is being sent to and pushed away, with centrifugal force.
Okay.
I see. Okay, so Archimedes' principle tells us that matter is sinking to the bottom of things, and centrifugal force is pushing it outward. Is what I see dense matter doing.
Okay.
Did I lose you guys?
No. I'm with you a little bit, but okay. So you're saying that we're spinning around. All right. So we to have centripetal force, you
Right.
have to be moving. Okay. All right. And you're
Right.
saying that things are dense and they're being pulled down. All right. But
Right.
the
Through
thing is,
space-time curvature acceleration.
it's like you're just wanting to ignore the fact that a lot of these forces actually do the things that they do because of, you can call it whatever you want. If you don't want to call it gravity, call it something else, but it's there. These forces actually do a lot of the things that they do because there's got to be a force that actually does pull these things together in a certain way. They have to happen. We can call it something else. I mean, if you don't want to call it gravity, I mean, I do agree that in many cases, gravity is an illusion. Okay, it is actually not as real as everybody describes it the way that we actually want to. Okay, because there is a pull. It is a very complicated subject. All right, it's not as clear cut. All right, as we try to actually make it. Okay, I do agree with that. All right, it is very it is very difficult, even for very intelligent, even for scientists. Okay, I mean, it took Einstein over 7 years to figure out that why things were actually happening the way that they were, and then finally he's like, you know what, crap, and that's when he actually finally came up with the idea of the new general relativity. He knew that Newton was not as smart as he thought he was. All right,
Right.
the only thing that I actually refer to Newton as is the laws of gravitational force. Okay, those are real. Okay, they actually do. In the basic sense of it, they are it just for mathematics and for empirical data and evidence. That's it. Okay. Other than that, his entire theory of why things are the way they are, we understand a lot of the things but we don't always know why they do what they do. Okay, that's where Einstein came in. He was trying to figure out, okay, we know this, but we don't know why it does what it does. So that's where he started coming up with, well, shoot, why does gravity work the way it does? Well, that's when he came up with the theory of general relativity. And it wasn't just, no, I won't go into that. But anyway, just
please explain your idea of what general relativity is.
Oh, well, there's several different parts to it, but I mean, we actually
we don't have 6 hours.
Yeah, we don't have all that much time. General relativity is very, very long, and it's extremely huge. It's just that one little part where it talks about. Go ahead. You were about to say something. You froze.
Oh no, you froze.
Would it be easy to simplify it to space-time curvature?
Give me a specific. Just ask me a question about it, and then I'll explain it.
Zachariah, it's you're a little choppy.
I think you froze, bud.
You're coming and going a little bit.
You still there, bud?
Yeah, I got you guys. I'm not
going
over here.
I'm mean or rude, dude. I'm just trying. Yeah, you're there. I'm trying to narrow down what you're trying to ask. Ask me a direct question. Because you'd say what general relativity is. We could describe that all day long. It would take forever. But what are you exactly asking?
Okay. Would you agree that space-time curvature acceleration is basically the theory of relativity?
Well, of course.
Okay. Yeah, that's what I was expecting you to answer as well. But we I'll use the word.
So, Zachariah, you are
and not a force.
Yeah, hold on a second, Zachariah. We didn't really hear. Something isn't quite right. Yeah, you were real good until just like a minute or two ago. So I don't know if something changed. Did your kids start playing Fortnite or something?
I lost him. He's gone. If you can still hear me when you come back.
No, I have full Wi-Fi here.
Okay. Let's try to narrow it down a little bit and understand why you feel gravity is not a force. Is that you think, McToon? You think that's a good one?
Yeah.
Sure.
Yeah. Okay. Let's try to work. Because I can go on a tangent on other things. Maybe we just need to focus more on that and understand more. Because I think that's where we're at. Where we don't agree. All right. So if you could explain this a little bit more and try to be specific and not as broad as, just be specific on why you feel it's not a force. Try that. And then, and then if you ask me a question, and then I'll go in there.
Okay.
And I can't hear you.
Can you guys hear me?
No.
Maybe.
I heard that.
Yeah, we hear you. Maybe if you turned off your video. Or.
Okay.
I mean,
yeah, there's a.
Maybe.
There you go.
Yeah, you can just do your voice.
Give that a shot.
How about now?
That's much better.
Okay.
I can't hear.
Got it. All right. So I believe
there you are.
I
can hear you.
You guys can't hear me?
Yeah, we're good.
No, I hear you. I hear you. I'm sorry. Go ahead. Anytime.
Maybe.
You guys are super delayed.
Oh, yeah. It's still something on your side there, Zachariah.
Oh, this sucks. We were having such a good discussion, too.
Yeah.
Maybe he should just reset.
Sorry.
Maybe.
Yeah, you could, Zachariah, you could try, like going out of it, and then I know you're on an Android or an iPhone, right?
Right.
Yeah, you could try going out and then coming back in and reusing the link, or just reloading the. Did it go to the Google Hangouts app? Is that what you're in?
Yes, it sure did.
Mm.
So let's see here. I'm gonna end the call and then I'll call you guys right back.
Yeah.
Yeah,
Okay.
please come right back, please. We're doing good.
Yep. I think it might be. It might be. It changed your screen is all zoomed funny. Let me.
Oh, me?
Yeah. No, don't worry about it. Maybe,
Oh, you're right. It did.
Yeah.
Son of a gun.
Maybe we could do why he thinks it's flat, because so far this has been kind of interesting, but not.
I know we're
not
on
into why it's flat, right? So
that's fine. I can get on a tangent pretty easy. That's why we have moderators.
Yeah. All right, Zachariah, how you doing there? Can we hear you?
Yes, can you hear me?
Sounds
Yes.
good. So let's give it a go.
I'll leave my video off for now. Should I?
Yeah. Yeah.
Okay.
All right.
Yeah, let's like maybe Tim was saying, let's go back to why you. I mean, there's so many questions, but I mean, yeah, we want to know more about why you think the world is flat by your understanding of gravity as a non-force in a geocentric system. So
Yes.
if you can explain that specifically, with that, as specific as you can, and then we can go from there. Does that sound good, McToon?
Yeah.
Okay.
Not being a force, if that's okay.
Now you're really soft, but go ahead.
Can you hear me?
Yep.
Yes.
Okay. I could start with gravity not being a force, if that's okay.
Please.
Okay with you guys.
We can. That's all right.
Yeah. So the way I see it is actually density. Density is time curvature acceleration downward into a Euclidean flat plane of what I perceive as a flat universe, which also means a flat galaxy, a flat solar system, and finally a flat Earth, right? So this Euclidean flat plane that's doesn't have all these warps and waves like non-Euclidean surfaces of general relativity say they do, but I believe in more of a general special relativity that you have centrifugal motion caused by space-time curvature acceleration, which is providing a gravity, a force of gravity or an effective gravity, however you want to look at it, on higher dense matter compared to low dense matter, right? And you have all this centrifugal action going on, spreading out the dense matter outward, away from the center of mass, the axis of rotation, and downward. You have it pull it through, down away from the actual axis of rotation. Basically,
Okay.
what
Hold
I
on.
see it as.
Time out. What specific force is actually causing this? Okay, is what I'm trying to, you're saying that gravity is not a force. Okay, there's got to be something that is actually causing it, and you cannot say that it's buoyancy. Okay,
it would be centrifugal force if you want to say anything else.
Centripetal force. There's got to be something else that's actually being used in this. Okay, something. Okay, what caused it to actually start to spin? What actually is keeping everything pulled together instead of being pulled apart? You know what I'm saying? You have something spinning around over and over, over and over again. Something is actually keeping it from actually flying apart. Am I being loud?
I don't see everything pulled together. That's the thing.
You didn't say nothing's pulling it together.
I said,
Is that
yeah,
what you
I
just
don't
said?
see everything as being pulled together. I see everything as being orbits. Like 99% of all matter is energy, right?
Okay,
And
if
it's
you actually have
energy in
something
orbit.
around and there's nothing pulling it together, then the only thing there is something pulling it apart. You understand what I'm saying?
I do, but do you understand that energy actually, like how proteins stack together and everything through energy, or how matter is created using energy?
Well, of course. I mean, E equals
Yeah,
mc squared. Is that what you're trying to go with?
right. Yes, exactly.
Okay.
You accelerate something faster than the speed of light, and it just starts becoming so energetically massive that it becomes matter and heavy, and you can't even, you
But what does
know,
that have to do with actually holding the planet together?
that's what I see as holding like atoms together, holding matter together, and holding all the things like science says
Okay,
it's
hold on. So
orbits.
you're actually saying that you don't actually believe in strong force, weak force,
And
electromagnetism, the
yes, I
law,
believe in
the
electrical
forces of
magnetic force.
attraction? There's four of them: strong,
Right.
weak, electromagnetism, and gravity. Those are the things that are the forces of
So the
attraction.
only one I have a question about would be gravity. Gravity
Okay, which is
is
the
not
weakest force.
actually pulling things to the surface of Earth.
Okay.
Yeah,
Well,
it
then,
would be the
I
weakest
mean, 'cause
force,
the
and it's
atoms
not
are being
pulling
held
anything to
together
Earth.
by
That's what I
strong
believe.
force. As long as they're within, what is it, 1 times 10 to the negative 15th meters, I think it is. I have to might need to look that one up, but I'm pretty sure as long as they're within that, range, the protons hold together. And we've gone on a tangent,
Right,
but
right.
I heard you say that,
Except for the fact of gravity.
okay. So you believe in electromagnetism, weak force, strong force, but not gravity. As a force, anyway.
Right. Yes.
And what is it?
As a
It's
force,
not
I
a
believe
force,
it's an
then what's
effect of space-time curvature.
okay, it's just an effect.
And how does it manifest itself?
It was
You turn your
space
video
would
back
be
on, and
pulled
hold on.
to the surface of the Earth.
Yeah, hold on a second there. Yeah, there, that's better. Yeah, it was good. As good as it would be to have the video, it's just not quite cutting
Okay,
it.
I'll just.
I mean, I'm not trying to be mean or rude. I'm trying to
All right,
understand.
no problem.
That's all I'm trying to do. Trying to understand.
Sure, no problem.
And
So say
I'm
you had
really
something
not
suspended
following.
in time and space, but it was still being
Right. I mean, you throw a
sorry.
lot of words together, but they're not all.
Can
all
you
of them.
imagine?
Go ahead. I'm sorry, you were saying something.
Yeah, can you imagine that you suspend something in space, but it's still being affected by time? So it's a space-time pulling something to the ground instead of gravity, you know?
That doesn't make sense to me. I'm sorry. I'm trying to understand what you're trying to say, and that doesn't
Yeah.
make sense to me. I mean, I understand everything is affected by time, but time is not a force. Time is just you start and stop. In between these time, you got here and you got there. Time 0 to time whatever. That's things happen in between that time. I
So
mean,
to me, time would be
but time is relative depending on no matter where you're at. Time is different in every part of the universe. Time on Mars is not the same as it is here.
Right, I agree.
I mean,
So, so our feet faster than our head.
I'm only getting every other word, man. I'm not. I don't know. Yeah, this really sucks. We were having a good one, too. Good discussion.
Yeah.
Uh,
Sorry about that, guys. Can you hear me?
no, it's not your fault, man. I'm not blaming you at all. I hear you every once in a while.
Yeah.
Maybe the satellites just moved.
I can hear you guys really clear though. That's weird.
I was muted. They didn't hear me. The stream didn't hear me, but you guys did. I was turning down my mic so I could do my cube, and you wouldn't hear.
No, you did good. I was watching you do that. I mean, maybe we can do this again another time or something. I don't know.
Yeah. Zachariah, where were you when you first started? Because that was the probably the best location.
Okay, I'm right on the bench. Is it clear now or?
Yeah.
I mean, I hear you.
Yeah.
I mean, it's just every once in a while it just gets a little out of there.
Yeah.
Yeah, it's probably because I'm in Alaska. That's just Alaska service for you.
Yeah.
Could be. Yeah.
Yeah. However it is. I mean,
it's somebody now.
Yeah, I'd like to know more about your about the buoyancy thing. If we are able to, if you're able to talk about that, and before I lose you again.
Sure. Yeah.
Start wherever you want.
Okay, so we got buoyancy, right? Archimedes principle of buoyancy. Basically,
Well, I mean, explain
fluid.
it works in space. Is what I'm trying to. Is what I'm wanting to.
So basically, what I see in space is plasma, a bunch of plasma layers of plasma, and we're sitting on top of the Earth is sitting on top of a layer of lava plasma. And on top of the lava plasma is the ground, the bedrock and everything like that. Then you have the air above that, the atmosphere plasma, which is also or water. You could also see water as a type of plasma. So you have different fluids, plasma fluids, that have different densities compared to each other. And it's when they're sitting in space-time, in the space-time warp, if you will, right on top of the space-time warp. Some of them are lighter and some of them are heavier than others. The ones that are heavier will be pulled down by the space-time warp, and the ones that are lighter will be pulled upward into the air, basically. All the way you have a layer of nitrogen, you have a layer of helium, you have a layer of hydrogen.
Where did you get this this hypothesis?
Just
ask that.
Just studying Actually, I got this hypothesis studying the makeup of the moon and the sun, and I read about how much hydrogen the sun is and how much.
Do you know the moon actually was part of the Earth at one time, right?
Yeah, that's what they tell us.
Well, it is. It's just a theory, but I mean, it's the most accepted theory. And the moon is round.
Sorry,
can you hear me?
Yeah, I hear you.
Oh, okay. I didn't know. I didn't know if you could hear me. A long time ago, I think a planet was it Theia ran into it hit the Earth, about 4 billion years ago, and it ripped up a bunch of ripped up the moon or the Earth, and then that's where it's the Earth. the moon started to create itself. And because, however you actually want to call it, the forces, whatever, it spun around and started forming together. And then that's where the moon came from. I mean, unless you have another idea. Maybe we're going
so my hypothesis.
That's a little off topic.
Go ahead.
Okay. Zachariah, you're saying something about plasma and the moon.
Yeah, so like I see the Archimedes principle of buoyancy applying to the moon as a plasma. It's floating. It has enough displacement volume to float above the atmosphere in the thermosphere, and it's just floating up there because of its displacement volume. It's displacing its weight and volume of atmosphere, of thermosphere, whatever you want to call it. It's displacing that, allowing it to float around up there is what I hypothesize anyway.
Okay.
So,
I don't even know where to go with that.
If you don't mind me asking, why do you think that the moon is made of plasma and that it's that buoyant instead of that it's a rock like when we bounce radar off of it?
Sure. So when I was researching about what's on the moon, we could go to the moon and mine helium, and helium-3 specifically. I find out that helium-3 actually has this really highly, when it's super cooled like the moon is, or superheated, it has these buoyancy properties that.
What has
but you
buoyancy
realize
properties?
There is so little of helium-3 on the moon. I mean, it is almost non-existent. Do you actually know the numbers?
From what I can
numbers.
Yeah, I've looked them up before, and I know like every day that it just gets bombarded with massive amounts of helium-3.
From where?
Just from the sun. Yeah, from the sun. From solar flares, it just gets bombarded with this stuff and embedded into the rock. And then I come to find out that actually, the surface of the moon is a dust-like particles of this stuff, and they float around, and that's what gives astronauts very high buoyancy on the moon. It's just like they're just floating around in this helium plasma, and they say it's gravity that's like low gravity of the moon that's causing this. But why does the moon have low gravity? Is because it's really buoyant.
You don't think maybe it's just because it has less mass than the Earth?
It would have less mass. Yes, you're right, because of my hypothesis is that it's plasma.
Okay. So you're saying that
plasma.
Because helium is lighter, that it's causing. Why is it lighter? If there's no gravity force, then what would make it lighter?
So helium is floating above the
so it's floating.
Nitrogen and oxygen. So it's helium is by nature lighter. Okay. And it's because of space-time curvature, acceleration effect of gravity, which is not a force.
Do you know where we get helium on the Earth?
Helium, we come from rocks inside the Earth.
In a sense, we get it from methane deposit or natural gas deposits.
Yes.
Which is mostly.
But they get trapped right inside the rocks of the
Earth. They get trapped inside there. That's right.
Yeah. So this is another hypothesis of mine, is that this helium trapped inside the rocks is actually making the Earth very buoyant, where it's just stationary in space above the black hole of dense matter. And it's not just helium; it could be any kind of lighter matter. It could be
let's
oxygen.
Go back to the black hole. Okay, how did this black hole get created, please? And why is it not sucking us? Do you know that if there was actually a black hole, even the size of, we'll say my desk, that it would actually destroy the Earth
it would destroy the Earth, but it would take an eternity to destroy the Earth because of time dilation, right? So that's how I hypothesize it.
Okay.
We are being destroyed as we speak. We just don't experience it yet because we're not close enough to the black hole.
But what is the black hole doing there? Why is it underneath us, and what is it doing?
It's just being pulled. It's basically warping space-time. It's all the dense matter of the universe collecting into pools, into these round puddles, or if you will, of dense matter, and sinking through the Earth, through everything, through the lava, through everything, into the space-time warp, and just causing that space-time warp. That's what I hypothesize causes it anyway.
No, it's a hypothesis. It's something. Have you done any testing to actually test any of these theories?
No.
Or hypotheses? Has anybody that you
I just study science. I just study science, and I say, well, if these things are real, maybe we could test. Someday we'll be able to look at a black hole. Well, we're just.
Do you know of any general relativity tests that have been done that have been falsified?
I don't know any that have been falsified.
So you believe that they are all correct?
Yeah.
The ones that have been done.
The ones that have been done have proven general relativity correct.
Yes.
Yeah. So.
And you do know that Einstein did believe in gravity as a force.
I believe he said it was an effect.
It is an effect, but that doesn't mean it's an effect that was created by space-time, but as we feel it, that's the effect. Right. I mean, it doesn't mean, it was created by space-time curvature, but it doesn't mean that it's not a force. He never said that. In fact, he said the opposite. Anyway, I won't harp on that.
All right.
Do you have any?
Do we need to end it here, or
I don't know.
Going?
No. I think that maybe we can move on. There was another. There's two other topics. Maybe one. We talked about, I think, how you can determine how far things are away.
Oh yeah, amazing! I love that one.
Yeah, maybe you could do that, and then Matt, and see what Zachariah has to say.
Okay, when we talk about parallax, or like what
whatever celestial object you want to talk about, how we measure the distance.
Well, first I need to. Okay, how big do you believe the universe is as big as we, as is scientists believe, or no? Do you think it's just a little small area, or that it's actually bigger, and that it's expanding, or whatever? Anything? Are you there? Did we lose him?
I don't know. I still see his icon is still there. Zachariah, if you're talking, we don't hear you.
We've actually done testing in the group. We've done me and Ian. We've actually tested. We've measured the moon. To see how far away it is. It's actually a really cool thing. Figured I'd just talk until he comes back.
Yeah.
My wife is calling me right now.
Oh, sorry.
Say
Got
hi
you.
for us.
No,
Hi for
she's
us.
the boss.
Yeah.
I understand. But yeah, parallax is a really cool thing. For those that, if nobody understands it, it's put your finger in front of you, and are you back?
Yes, I'm here. Can you hear
Okay,
me?
I'm sorry. It saves me from actually having to just talk.
Matt, if you could, you're a little soft compared to him now. I think something changed with his audio, so if you could move your mic farther away or something.
Okay, I'll just back up. Am I just loud?
I think that might work.
I'm a loud talker, so.
All right, we'll keep going then.
Are you there? Okay. You want me to talk or wait for him? Or?
Yeah, go ahead, Matt.
Go ahead.
Okay.
Here.
Oh, well, go ahead.
No, you have the floor, Matt.
Oh, I have it. Okay.
Yeah, and measuring distance to some celestial object.
Okay. All right. How they actually measure distances to just it depends on how far away that things are. We've actually done it, in testing. You can actually measure the moon's distance very simply by something called parallax. All right. It does take a little bit of math, calculus, but the simplest way to actually explain it, if you put your finger up in front of your face and you close one eye and then you close it and then you open the other one, and the differences between it, you can actually measure. You can end up using math to actually determine how far away your finger is from your face. All right, and they do the same. It's very simplistic, but that's how you can actually do the same thing with the moon. I actually, even when I was a kid, that's how I actually I measured, doing the same thing with the sun, and that's how we actually determined, 3,000 years ago that we actually orbit the sun. They did the same thing, and you have to do it over a long period of time, but it's really cool. I actually have the math. I can send it out. But it's a really cool science. But but nowadays we don't do that. We use radar, to actually, do like close things, like the planets. We do measurements, use parallax for stars, faraway stars. And then the further out we get, I don't remember. Ian, I think you're listening. Let me see. What is it? The further things out, we use a different technique. What is it? Type A1 supernova, cephaloid, variable star, Doppler shift. I can't remember. But anyway, we used parallax for mostly things that are further away. But because we have radar now that we can bounce things off of that are a little easier. But to actually do simple, so you can actually understand it yourself, we can try that. It's if you have as long as you have like a telescope or just a camera, what you do is you take a picture of the moon, and as long as you can see the stars around it, and definitely identifying those stars actually can help. But you do that, and then you have a buddy of yours do the exact same thing at the exact same time, somewhere else, as long as it's at least a few hundred miles away. And then he takes a picture of it, and then you compare those. You have to know the exact distance between you and your buddy, but you compare those stars, that shift, and then you can actually determine it. And we have done it before. It's very simple, and that's how we actually, I think we come up with around 300,000 kilometers to the moon. But it does vary, between 200 and 400,000. Anyway, is there anything more you wanted on that? Or was there something else you wanted to?
So that's how we measure stars. Zachariah, yeah. What's your take on our solar system? Where's the sun? Where's the moon and the planets? If they are not flat, they're not just wandering stars, what are they and how does it work?
Right. They would be above Earth on our ellipsoid, right? of an Earth, which has all the landmass on the surface, and then they're very light, very buoyant, and they would be floating in the thermosphere, is what I hypothesize. And the one thing that I would say about parallax is why pilots, when they're flying along, have to look at their instruments straight dead on instead of at an angle from their seat, is because the parallax causes them to give a bad reading on their instrument, So that's what the little I do know about parallax. I know it's not an accurate assessment of distance. Now radar, I would have to look at radar. I've never heard of that. I'll take that into consideration. I would like to study how we would use radar to measure distance of the solar system, solar body.
They send out signals, and then it bounces back, and then they measure the time that it's out there, and then the time that it comes back.
The time. Wouldn't you consider time dilation, because time is really fast in outer space, and then as it gets closer to Earth, it slows down. So wouldn't you have to take that into consideration?
No.
No? I wonder why.
Well, I mean, that's not exactly true. There is, yes, okay.
There's nothing in space, really, essentially.
You have to take a little bit into consideration, because the further away, time does actually slow down the further away you get from Earth. Yes, that is very true. I'm sorry. Reverse that. Okay.
Right.
Because like with satellites, but it's very, very small. Okay. But yes, like there's actually a time correction. That's why it takes 4 satellites to actually do GPS. All right. You have the 3, to the triangulation, and then you have the 4th one that they actually use to that actually does the time correction. Okay. But it's so small, but it does make a difference for actually GPS. But the time correction is so small for what we're talking about for measuring.
I would think it would be magnified, because we're measuring distances.
It's nanoseconds. Right? It's nanoseconds.
Nanoseconds. Okay.
That's it for the time trick. But yes, they actually do have a time correction that they use.
A time correction, yeah.
Yeah, it's just a mathematical thing that they use.
Yeah.
I can send you the information on that if you'd like.
Right. So
actually,
with
really cool math that they used.
GPS is quite involved on the whole system is well done. So
there's 31 satellites, I think. 33 satellites, I think there is for GPS.
So
and they have to have six satellites that are always available at whenever.
Yeah,
they do
for backup. So Zachariah, do you think the satellites are up in above the Earth somewhere?
Yeah, they would be in the exosphere.
But how do they stay there?
It would be that space-time curvature acceleration pulling them along, and they're highly buoyant. They displace their weight and mass. Have you heard of buoyant reentry?
How can they be buoyant if they're in a vacuum?
They're really heavy.
We have ways to use gases to make them buoyant and stuff. If you expand a gas out in a volume, compressed gas out in a volume, it will make it very buoyant. So we send gas out
into space to keep them buoyant?
Not into space, inside their vessel, and moving gas around and stuff.
So,
from a compressed state.
Okay.
Sorry, go ahead.
No, go ahead.
Yeah, they're heavy. Like helium. It takes a lot of helium to lift something small. It's significantly different volume to lift something than than just the size of it. If you saw the Mythbusters did a great job. They The number of balloons that they needed to lift that little kid was ridiculous. I don't know what technology you think is doing this.
How helium works?
So you have hydrogen or helium or different things. Hydrogen is. Have you ever heard of atmospheric reentry, where they're using buoyancy to reenter the atmosphere instead of, to slow their speed upon reentry of an atmosphere?
No, I have never heard of that.
That's one of the things that rockets use, or satellites even use. They make themselves very buoyant in order to re-enter the atmosphere at a slower rate. Because if they were to re-enter the atmosphere at the rate they're going, they would burn up immediately, through friction.
But why? Do you know why they would do that? And why they would have to slow down? And why they're actually, what's pulling them down? And are they just falling?
So it would be, in my idea, it would be space-time curvature acceleration pulling them down.
But
through a very high.
You just
atmosphere.
You just said the definition of gravity. You realize that, right? You just didn't say the word.
Right. So gravity as an effect, which I call it space-time curvature acceleration rather than gravity.
That is what it is. That is gravity. You just called it.
I agree.
You just defined it instead of saying the word.
Okay, so we'll say gravity from now on, as long as you know space-time.
But it's a force. But you just okay. All right.
It's an effect of space-time, right?
But it's a force. You just said it. You said it 4 times in the last 30 seconds.
This is where we'll have to agree to disagree.
All right, Bubba. All right. Oh man.
So hold on. So as you go up in elevation, you know this. You're airplane mechanic. There's less air, right? The air pressure goes down, and it continues to go down as you get higher within elevation. So buoyancy is achieved by but by displacement, right? When you have something at sea level and you fill a balloon, right, with helium, the air is more dense than what's in the helium balloon, right? So the air says, get out of here. I want to be below you. And that's what pushes it up. When you get up to the thermosphere, there isn't hardly any air. There's so little air that there isn't any more buoyant force that's appreciable, right? It's too weak. So so you need more and more size to get that same buoyant force the higher you go. There just isn't enough available to have it just float there, right? Because satellites, there's a lot of circuitry and batteries and dishes and solar panels in them, right? They're thousands of kilograms. So we don't really.
If you consider,
So all right, so we don't really have a whole lot of opportunity to reduce their effective weight through some sort of a buoyancy trick.
Right. So consider like G-force, right? An airplane in parabolic flight, it goes upward, right, to counteract the force of gravity pulling it down, and then it can become weightless for a moment right at the top of the parabolic flight before it heads back down. So if you think of the same thing, space-time curvature accelerating the satellite through space at such a fast rate against the force of gravity, we'll say, pulling it down, it will maintain an arc, weightless, buoyant arc, around the surface of the Earth instead of being pulled into the surface of the Earth.
Yeah, we have a name. We have a name for that.
You understand what force is, right? Force equals mass times acceleration, right?
Right.
Okay. And space-time, we'll just call it gravity. All right. Gravity is an acceleration, right?
Yes, it's an accelerating force. Yes.
Force. Thank you. Thank you very much. All right. Mass times acceleration. All right. And acceleration is a force. Okay. I don't need to go any further with that one. I want to go
All
on
right.
to this next thing.
We'll let you win that one.
Thank you so much. Archimedes' principle. Okay. I'm actually going to read it to you. Okay. All right.
Okay.
States that the upward buoyant force that is exerted on a body immersed in a fluid, whether fully or partially submerged, is equal to the weight of the fluid that the body displaces and acts in upward direction at the center of mass of the displaced fluid. Archimedes' principle, anyway, that's the entire, that is the basic explanation of it. Can you explain to me
what would you consider a gas a fluid?
Are we going to say that gas is a fluid?
Yeah, that's my question.
Okay. Well, what is it? So you're saying gas is a fluid?
Yeah, I would say gas is a fluid, but I'm asking you, would you agree?
Have two different weights of fluids and put them, two different gases and put them together, and they can, I can see what you're saying there, but it is not a liquid.
Right, not a liquid, just a fluid.
All right, so we're saying that, well, how much gas do you feel is floating around where satellites are?
Again, I would agree with you. It's not very much at all. It's very, very little, almost vacuum-like. But I would say the speed,
almost vacuum-like.
Yeah, the speed that the space satellite would be going at would counteract any space-time curvature acceleration, making it weightless. Basically, is what Archimedes' principle. It's displacing that weight. So it doesn't take very much fluid to displace that kind of buoyant weight. You see what I'm saying?
Yes. I am seeing what you're saying, and I think you're actually starting to agree with me and say the exact same thing that I'm saying.
Okay. Well, like, that's the whole thing about the flat versus round Earth debate, is like all these principles that you guys agree with would still apply on a flat plane. And I just am distinguishing from the idea that, okay, maybe there is a flat surface that these principles can apply to,
But the idea is how did it become flat and not round? You understand the point that we're just at, because you've already agreed with me that gravity is a force. Whether you actually want to accept that or not, you've said it several times, and you've accepted it. Whether you want to accept it or not out loud is understandable. But
I'll say it out loud.
The idea of what causes things to actually become round is because of the force that pulls them down as they spin. The center of mass, or the center of gravity, that actually pulls things towards the center, the strongest part or the most mass that there is. Things are pulled towards it. We build cars that have center of gravity, because we don't want them to flip over because of the center of gravity. All right. That's why they actually are very particular on where they put that center of gravity. All right. And that's why when things are spinning, things start being pulled together and pulled down and tighten and tighten and tighten all the way down until they actually become we'll just say sphere, okay? Something that ends up being round, because everything starts pulling tighter and tighter all the way around. All right, that's what creates.
That's where I would disagree with you.
Now, if things spin fast enough, super fast, I mean, it would have to be extremely fast, which some people actually laugh at the fact that we're actually moving as fast as we are. Then they will actually start to they flatten in a sense, but it would take a lot to spin that fast. You know what I'm talking about?
Oh yeah, that's.
But we're not moving that fast. Not as fast as
I
it
don't
would
see
actually
how
take.
it could go from being pulled in to pulled out. That's where I would disagree with.
It
How do you
happened.
distinguish at which point it starts getting pulled in versus being pushed out?
No, I said flatten. If you spin something fast enough, it will actually do that.
Right, exactly. My question is, okay, you're saying things spin around on an axis, right? In space. Okay. Now, what causes it to
spin?
Yeah, are you there? I'm here.
No, I'm saying I'm sorry. I spoke too fast.
What causes it to coalesce around this axis? Why doesn't it fling out like a merry-go-round,
Well, yeah, that's what I asked you earlier. Whenever I was saying how, if you spin it around real fast, if there's not a force that is pulling it inside itself, then it would actually just, release. Fly apart. Yes, thank you.
Right.
So
that's what I was saying earlier.
We can calculate the centrifugal force.
So I would say,
we're not actually rotating that quickly. The raw miles per hour seems daunting, but the angular speed is very slow. So it's somewhere around 0.02 meters per second squared. And you contrast that to the 9.8 meters per second squared that we measure all over the surface of the Earth. So that's actually a combination of both the force of gravity and the upward force of centrifugal force. So it's 0.02. It's just not that much.
No.
Yeah. See, I just don't see how a gravity would apply to a spinning mass. I don't understand that at all.
Well, it doesn't matter
because
if it's spinning.
That keeps it from flying apart, is what we're trying to say. Or definitely what I'm trying to say, is if you spin something around, I don't know how to say it any different. I don't. I'm at a loss, I guess.
Yeah.
Okay. So a black hole would be very dense, and I would say the center of it is not spinning very fast at all, right?
Infinite. A black hole is considered infinite mass, right?
Infinite spins?
No, mass. That's why it's so.
So you think a black hole is spinning at an infinite amount?
No, that's not what I said. I'm saying that it's considered infinite mass. It's
No, I think the density is what we're talking about.
Right.
Or density. Anyway, go ahead. Say what you're saying, Zach. I'm sorry, I didn't mean to interrupt you.
No problem. So you got the black hole in its warping space-time, right? But I don't see that as a spinning point. I see the time warp and everything around it, all the matter around it, as what's spinning around the black hole. Warp, So
it is dense.
That's more of space-time curvature warp, causing a centrifugal spin that is actually pushing heavy, dense mass away from a black hole as it gets further out.
Okay.
But that's not what we see.
Would that make any sense or no? What do we see? How are you saying we see it?
No, go ahead, Matt.
No, I'm just. Can you say the last thing you just said again? I'm sorry.
Yes. So you got the space-time curvature being warped, causing a spin around a black hole of all the other mass that isn't a part of the black hole.
Okay. And what is it? What are you trying to say that has to do with?
I was saying that
What is the point of it? Is
it's
what I'm
actually
trying
a
to say.
force that pushes, that counteracts the force of the black hole warping space-time, into it. That
Okay.
centrifugal force starts acting as a buoyant force and pushing things out, away from that center of mass,
But only if they're moving.
center of gravity, or whatever.
Okay.
But you don't see space-time as moving. Space-time as causing moving through, of objects.
Just because something nearby is spinning doesn't mean that the space-time around it is spinning. I don't think, and it certainly wouldn't impart centrifugal force to something nearby unless that thing was actually moving around in a circle.
Okay. So these black holes that are underneath this, you're saying that they're spinning?
No, they would be pretty much stationary, except they're.
And why are they there? What put them there, and why are they underneath us?
Well, it would just be energy manifesting as highly dense matter, and as energy manifests as denser and denser matter.
Okay, everything in physics has a balance. All right. I mean, you could say physics is lazy. Okay, it always tries to find, the simplest and laziest way to actually get to a certain point. Okay, so it finds a balance, whatever the balance is. So for those things to have been there, that means that physics wants them there. Okay, that's what I'm trying to ask. Why are they there, and what put them there, and what is their point and purpose for being there? They had
the physics that put them there would be Archimedes' principle of buoyancy and density, right?
But why?
So I don't know if we can come to a why.
Well, maybe not.
That unfortunately is not testable.
It has to actually be doing something. So, if that's what's actually creating our gravity, is that what you're trying to say?
Yes. That warping of space-time of black holes is creating gravity.
So that's what's creating our gravity here.
Yeah.
All right, so
that would be our gravity and every gravity that ever exists in the universe.
So a large, massive black hole that's infinitely dense is the reason why we have gravity.
It doesn't have to be very large. It could be pretty tiny. Infinite mass, but very dense,
It's not mass. I did look that up. I was wrong on that. I apologize. It's infinite density. What it is. I apologize.
Infinite density. Okay.
I'm allowed to make mistakes.
No problem.
Yeah, it's density. I don't even know where to go with that. What?
This is what a debate is for, but it's just
why is it easier to say that we have black holes than just say that we have that mass attracts other mass?
Because that makes
a huge black hole in the center of our galaxy. That is true. That's why it's a spiral galaxy. Every spiral galaxy has a huge black hole in the center of it. Every one of them.
I see some mass that doesn't attract, some mass repels, I see different types of mass.
What mass doesn't attract?
Or I see buoyant mass.
Hold on. Time out. Explain that. This is going to be a long discussion, I see.
What mass does not attract?
Yeah, that's what I was going to say. Go ahead.
Helium gases, the
So you're saying helium doesn't attract anything else? Because why?
It
because
balloons go like 1,000 pounds of helium,
not just
that it would not attract.
It's Archimedes' principle. It's just Archimedes' principle.
Okay.
That's all.
Okay.
So
yeah,
go ahead with that.
Go ahead.
So yeah, it displaced something else that was more dense. Right? That's what the balloon did. It displaced the air. The air is more dense. So Archimedes' principle says the air wants to say, get out of here. This is where I'm going to be. You need to be higher than me. Helium isn't repelling anything. It's just not attracting it as strongly.
But the reason why helium actually floats is because oxygen is heavier and being pulled down faster than helium is actually being pulled down. That's the reason why it rises. That's the whole point, is just because of gravity. I mean, I could.
So you're saying,
explain it a little better if you'd like. The whole reason why.
I mean, okay, we can say, yeah, you're right. It's gravity causing denser oxygen to fall below helium, which is pushing the helium right away, which is, repelling, acting as a repellent or a, displacing force, if you want to say, but it's not being.
I mean, it is buoyancy that the reason why. I'm not denying that, but it's because of gravity that's actually the main force that's actually pulling on it. I'm sorry. Go ahead.
Yeah. So
I didn't mean to interrupt.
For me, it would be the space-time curvature acceleration pulling the oxygen molecules, toward the black hole is what I see in denser matter causing that warp of space-time, and it's all connected, all interconnected, buoyancy and gravity through that space-time curvature acceleration.
You like that word? You like saying that instead of gravity, huh?
Okay. I love that word.
Okay.
Can I? Here's.
We're gonna have.
Maybe we need to start wrapping things up.
Well, I have
died on me as well.
All right, go ahead.
Well, maybe I don't know if we can get into this or not, but so.
All right, well, go ahead.
My question to you, Zachariah, is why all this stuff was circular around the core thing of why do you think the Earth is flat?
Okay, so it would be the centrifugal force that would cause it to be flat and not anything else.
Because we're spinning?
Because space-time is spinning, pulling all the denser mass out away from the center of the axis of the spin. And it's not us that's
not how it works.
It would be the space-time curvature that's spinning.
I told you that we would have to spin extremely fast for that to happen, and we're not spinning that fast. We would have to be spinning. I don't know. I don't even want to actually guess at it, but it would be extreme.
Yeah, much. The
only way that would happen. We would,
but that spin would be causing buoyancy, right? Buoyancy would be
our days would be like seconds.
Okay.
I mean, it would be
all right,
for us to be that fast.
So I don't think that you started with that as your idea for why it was flat, right? Well, there must have been some other thing that brought you to think that the Earth is flat.
So the other thing is, all right, that spinning of space-time is causing a layering effect, a sediment layer where lighter matter is on top of heavier matter, and it just layers in a flat scheme, whereas I don't see how that would apply on a globe. I don't see a globe having that kind of mass at the center of it to warp space-time all around it. I don't see anything being able to exist down the bottom of a black hole, basically. I see
try to assume
everything existing above a black hole.
Well,
Okay. I, another clarifying question, if I can. Was this how you first started thinking the Earth was flat? Was because of this idea?
No, I started thinking the Earth was flat just based on like horizon, and I watched the movie The Principle, as a geocentrist, and thinking, the Earth is the center of the universe. And then I looked at general relativity, how that's possible. and I've just been a truth seeker all this whole time, and I haven't come to know any conclusions on any of it. I'm just, it's a debate, and I'm presenting a hypothesis that might be possible, and I could be completely, wrong. I'm willing to accept that as well.
Okay, so you are an airplane mechanic, right? Is that, I don't know what your exact title is.
Yeah.
Right.
AMP, licensed AMP.
Okay. So, airplanes, when they do great circle routes, right? So the distances,
right,
and the courses, from people you work with, they know that all of these things that they do requires it relies on the Earth being a sphere, right? I have over here, these are flight charts up here. There's two of them. There's a third that's in my closet over here that together form a triangle that has 270 degrees in it, something impossible on a flat surface. And they're just regular flight charts. These are real, you could really fly these
Have
routes.
you ever went into a flight simulator? I'm not a pilot, but I've been in a few flight simulator games.
Sure. Yeah.
And they're always flat. There's
but
never
we're not talking
any curve to them or whatsoever.
But that's not
and
what
as far as
pilots
pilot
do.
training goes, I've never heard them even consider the curvature of the Earth in any of their training, and
except when they plot routes, right? Their routes require them to use
I understand
maps that are projected from a
everybody has their
spherical
own,
source.
Focused field of study that they have to look at, and
so
as far as those kind of great circle routes, I would see that as space-time of aiding them. Oh, sorry, I'm sorry.
No, go ahead. Do they have a space-time switch on their on their app?
I believe those same maps that are from a oh, sorry, are you there?
No, yeah, keep
You're
going.
cutting out.
I'm sorry, I hit my camera. Go ahead.
Dang it.
We hear you, Zachariah.
You still there, bud?
I heard him say, "Dang it, something happened."
I lost you.
Maybe he dropped his phone.
Could be.
You okay, buddy?
Yeah.
He's talking to somebody that's not us, maybe.
Oh. Okay.
All right. This is it's interesting that somehow the space-time
Space-time centrifugal force of acceleration or something like that.
Yeah, you lost me.
and buoyancy.
No.
Yeah.
My phone's dying.
Oh, okay.
It's all good. It's all good. We can pick this up another time. I'm sorry. I think we've accomplished quite a bit.
Yeah.
I think.
Yeah. So how about let's move forward and just maybe kind of start wrapping it up. Zachariah, do you want to say some closing stuff and so we can wrap it up? Oh, first, can you hear me? Can you hear me, Zachariah?
I don't know.
I don't think so. All right. Well. Oh, there's a door. A kid.
Oh.
An air siren. Something.
Thank you for having me, though.
Yeah, thanks, Matt. Yeah, why don't you... I put a link to your... I'll do it again.
All right.
Oh, here we go. We got...
Thank you guys for having me.
Okay.
Can you hear me?
Yeah, we can.
Yeah.
We had a request you of Zachariah. If you were from Hawaii, people asking for a chihu from you.
Not really.
Not really from Hawaii. Okay.
Okay. What is a chihu?
Chihu was...
I don't hear you.
Oh. Darn it.
Oh,
I think he's answering somebody else's question.
I don't know. Is there any questions that anybody has for me, or anything? I'm trying to look at it as well.
Look at the chat here. Okay, so I'll put up plug your Facebook channel at least, or group.
What now? I think we lost him.
We did. Hold on a second.
Okay.
I gotta fix. So, all right, yeah, go ahead with your.
No, no, I thank you for. No, everybody's saying it was a polite debate. Very much so. I think we did a good one. I've been in some that are pretty brutal.
Yep. Here, I'm trying to get you on the screen, and OBS is disagreeing with me. Here, we get your ear.
Oh, you have my ear?
Just get your ear. Hold on. I gotta
Okay, I get mine. Mine is showing me straight up.
Let's see.
I don't know.
There we go. Oh, I'm gonna get it. OBS is sometimes tricky.
It's all good.
Oh, all right. There we go.
I think it was a good debate.
It was. He's a nice guy.
I didn't know. Are we still live?
We are live.
Okay.
Yes. So, well, that was we've certainly had some strange ideas, and but I think they're ideas, and instead of saying this is how it is and you're wrong if you don't accept it, he was saying I think I have an idea, and
yeah,
I think that's the way that we can move forward. So thank you to Zachariah. He is moving soon. He's in
yes.
His Facebook said Hawaii, but he's been in Alaska, and now he's moving somewhere else. I don't know if he's said that or not, so I won't say it, but he's moving somewhere else to be a mechanic somewhere else. So
yeah,
it's a kind of a portable job, I think.
Yeah, they got to fly around.
They do. There we go. Got that. Just thought I'd
little compass
that.
there.
Yeah, compass. There's
Yeah. Unless anybody has any questions, it's been good.
Yeah. Little different debate.
I mean, I tried my best to understand what was being stated, and I think we got him to believe in gravity. So that's
no,
good.
he kept denying it. I don't know.
At least gravity as a force. I don't know.
Yep.
It was a good. I had fun.
Yeah. Well, everybody, if you like this, want to see some more, I have a debate every Tuesday at 8 p.m. or, sometimes it changes, but click, subscribe and click the bell, and a little thumbs up on the video would be great. I have next week Tim Osman from Infinite Plane Society, not the other Tim Osman. So that should be good. He had a debate with Fight the Flat Earth a couple weeks ago, and it was pretty good. We're going to maybe pick up where they left off. So Bill Smith has a question. Since the Earth is flat, how can we see so far? He's perspective. Yes, that's the reason. So Matt Duckworth, plug your channel if you like, says Surf. Yeah, you do have a YouTube channel.
Yeah, I do. I'm gonna do more on it as well, and I'm gonna put this on there if that's still okay.
Oh yeah, you can mirror that.
I'm just gonna, as it is.
Here is the Facebook group I just posted in there.
But I do a lot more than just talk about flat Earth. I do a lot of science stuff, chemistry, some physics stuff, rockets, different things like that. Electronics a lot, yeah. But I don't always to talk about flat Earth because it always sometimes gives me a headache.
Yep.
There you go.
So there's the two links in there for people that want to look. So yeah, if you're on Facebook, people, pop in there. And I did put in a one for the JM Truth. Somebody made a JM Truth Facebook group that's not JM Truth. It's pretty funny. He got really upset. He posted in there really angry. He's gonna sue or something because the name. Hold on, I'll pull it up. The plane. No, that's not it. What was? My goodness. The Plain Truth. What did he call? I can't find it now. Did it go away? It wouldn't have gone away. Nope, that's not. I don't know. I put it in the chat earlier. Go find it. Go subscribe. It's pretty good.
Good.
The Plain Truth documentary. That's it.
There we go.
So look that up.
Yeah. Go ahead and add the page to our group, if you don't mind.
The Plain Truth.
No. Hold on. Let me see if I can.
There it is. The Plain Truth documentary. So the Plain Truth documentary is the name of the movie that JM Truth is making, and so this Facebook group is not JM Truth's group. So
Gotcha.
He got all upset. So all right. Well, that's what I have for tonight. Thank you, Matt. Thank you, Zachariah. And
anytime.
Yeah. All right, people. We'll see you later. Bye.
Thanks, guys.